So let us go over various search algorithms. But before that, there should be some benchmarks or evaluation criteria for evaluating these algorithms. The first one is optimality. So optimality deals with whether an algorithm is able to find an optimal solution or not. In some cases, an algorithm may find a solution, but it might not be an optimal one. In certain cases, an algorithm is guaranteed to find an optimal solution. An example is A-star algorithm. There are some cases when an algorithm is not even able to find a solution. In such cases, we say that that algorithm is not complete. So if an algorithm is able to find a solution 100% every time, then we say that it is complete. The third criteria is time complexity. So again, time complexity deals with the amount of time that an algorithm takes to find the solution. The space complexity deals with the amount of space that an algorithm requires to find the solution. Let us now look at breadth first search. So let us consider a very simple example, the problem of finding food. So the agent is present in the cell H and the food is present in cell C. So the agent does not know that food is present in cell C. He has to find that food and eat it. So how does breadth first search work? So essentially we start with the start node. We add it to a queue. After we've added it to a queue, we look at all the neighbors of H, that is G, E and I. We remove H from the queue and we add all its neighbors to the queue. Right? Now we've got E, I and G in the queue. The first element in the queue is E. We remove E from the queue and add all the neighbors of E. In this case, we have D, B, F and H as the neighbors of E. If we take left, we go to D. If we go up, we go to B. If we go to the right, we reach F. And if we go down, we reach H. But H has already been visited, so we'll not be adding any node that has already been visited. So in this case, we add D, B and F. So D, B and F have been added. Now the next node in the queue is I. We remove I from the queue and we add its neighbors, all those neighbors that have not been visited previously. So in this case, F and H have both been added to the queue, so they will not be added again. Now we go to G now. We remove G from the queue and we add all its neighbors to the queue, but D and H have both been added already. Now we go to D and add its neighbors. In this case, A is a new neighbor, it has not been visited, so it will be added. Similarly for B, C will be added. Now F will be removed from the queue and none of its neighbors can be added because they've already been visited. Now A will be removed from the queue. Similarly, C will be looked at, but now C is the goal state, and now the agent understands that we've reached a goal state and it stops there, and this is where we found our solution. The algorithm for breadth first search is as follows. So firstly, we'll be declaring some data structure, that is, there will be a queue that we'll be using and we'll be using a graph. So before that, one peculiarity of breadth first search is that it transverses a graph level by level, and the queue data structure helps us carry out this procedure. So there are three states in which a node can be present in. A node is unvisited if the node has not yet been seen. A node is visited if the node has been seen, that is, it was inside a queue at some point in time, but not all its children have been seen, and it is not expanded. And the third category of node is an expanded node. So when a node has been removed from the fringe and all its children have been added to the fringe, that is, all its children have been visited, then that node is expanded. You could just use unvisited and visited, but here I'm being more explicit by adding another state of expanded. So the algorithm starts like so. You add the start node to a queue, to an empty queue, and you mark the start node as visited. And then you keep iterating over all the members of the queue unless the queue is empty. Firstly, you remove the first element from the queue, you remove the first node, and we'll come back to this later. So if the current node is essentially the goal node, then we just collect all the parent nodes and then we return the collected nodes. We'll discuss more about this in a minute. But after current node has been dequeued, we'll iterate over all the adjacent nodes of the current node, or all the nodes that are reachable from the current node, and that can also be equal to all the outgoing edges in a directed graph or normal edges in a normal graph. So we iterate over all the adjacent nodes and we check if node n is visited. If it is unvisited, then only we add it to the queue and then we mark it as visited, and here we set the parent of n to the current node, because we've come to n through the current node, and we keep doing this for all the nodes in the queue till the queue is empty. And here we, in the end, after we also mark the current node as expanded. So at some point in time, if there is a goal node, if a goal node exists in the graph, we will reach this stage. And in that case, what we do is we collect all the parent nodes, we iterate over, we essentially backtrack and find all the parents, and then we collect all those nodes, we store them, and then we return those nodes. Now this is essentially a solution, right? Solution to breadth first search. Now let us analyze the time complexity of breadth first search. So this while loop, this will execute v times because it processes every single node at least once. So now v is nothing but the number of nodes in the graph, and this node, that is this for loop which is present inside this while loop, will run ev times. So ev is nothing but the number of edges for the vth vertex. Okay, so in this case, so this is the second vertex, and in this case we will have two outgoing edges. So e2 will be 2 in this case. In this case it will again be 2. In this case it will be 1, and in this case it will be 0. So our algorithm runs v times plus the total number of edges times. That is, this is the number of nodes plus 2 edges for this node, plus 2 more edges for this node, 0 edges for this node, and 1 edge for this node, which means the time complexity is 9 in this case. But to generalize, I think you can write it this way, that is, the time complexity will be equal to big O of V plus E. Coming to the space complexity of breadth first search, imagine a scenario wherein V7 has just been removed from the queue, and in that case V14 and V15 will be added to the queue. So this at this point in time we will have the largest number of nodes in the queue. Therefore this can be generalized. So in this case the depth of the tree is 3, therefore 2 to the power 3 is 8, and we have 8 nodes in the queue, that is all the nodes in the last level. So the space complexity will be b to the power d. So b is nothing but the branching factor. So in this case the branching factor is 2 and the depth of the tree is 3. Therefore the space complexity will be b to the power d. Now yes, is breadth first search optimal? And the answer to that is yes. So I will quickly show you a demonstration here. You can play around with this project by going to this URL, and also contribute and implement some more algorithms if you want. So I'll set this as the start state, this as the goal state, and this as another goal state. So we have two solutions here, and the optimal solution is this, right? So I will select breadth first search and start the algorithm, and in this case it indeed finds the solution that is closer to the start node. Now let me just make this an intermediate node, a normal node, and make this as a goal state. So now let us see what happens in this case. In this case it finds a solution that is again closer to the start node. Now is BFS complete? And the answer is yes. So BFS always finds a solution. It will, unless the branching factor is infinite. So there are like infinite nodes after in every level, you won't be able to find a solution. But apart from that, if the branching factor is finite, a breadth first search should be able to find the solution, because it goes level by level, and there's no chance of it getting lost anywhere. So it might run out of memory, but it will find a solution if its memory is enough. Okay, so that's it. In the next lecture we will discuss about some other algorithm. Do visit this site and try out running certain algorithms.